All right, everyone, welcome back. In this video, I want to talk about circuits in parallel rather than series. So what I've done in this particular case is rather than drawing the picture of a battery, I've actually drawn a voltage source. So what this basically does is it creates a voltage difference of however many volts we have. So in my case, I'm just going to put 9 volts. And of course, I've drawn the similar water analogy, except this is now a 9 unit pressure generator, a UPG, I guess, would be what is created here. And now we want to think about what happens when I have two particular things. Now, let's simplify this. And in the first case, let's say case 1 is when R1 equals R2, and both of these equal 4.5 ohms. And let's just imagine here that our water, the diameter of these little resistors, the water resistor is sort of a place where the diameter shrinks, and of course this value here is going to be 4.5. So what actually happens in this particular case is water is going to, and remember that what happens when it goes through this pressure generator is you're going to have some amount of pressure. So coming up here, if I was to, for instance, probe the water pressure here, I would have 9 units of pressure, and down here, if I was to probe it, I would now have 0 units of pressure. So what's happening is all of the units of pressure are being sort of dissipated among R1 and R2, except now we've routed them in parallel rather than in series. And if we see in our voltage source thing, we see the same exact thing. Now, the thing to keep in mind, the thing that I want you to appreciate in this case, is that now we actually have two paths that the water can take. And as a result, we should expect this 9 units of pressure being divided up among R1 and R2, because both of these are going to see 9 units of pressure. It's not the case that there's less pressure. So what happens is actually the flow is what changes rather than, in this case, the pressure itself. So in our case, the pressure is decreased whenever we encounter resistance. Now, at this point, we still have 9 units of pressure, and as a result, we have 9 units of pressure that must be dissipated across R1 and R2. So now what we can do is we need to know that whatever the flow is here, whatever my flow is, and my flow coming in, it's going to be divided among this. So we can imagine this being F1 for flow 1 and F2 for flow 2. And whatever they do, they must be added together and combined to get my overall flow that goes through the pump. So a few things to note is flow is going to equal F1 plus F2. So let's see if we can find out what F1 and F2 are, knowing that our 9 units of pressure are dissipated across R1 and R2. And notice how this is the exact same thing here. In this particular case, this is going to be I. This is like I in terms of amps. And then you're going to have I1 and I2, where I is equal to I1 plus I2. So we're adding these together, and then at the end, basically, this I must divide itself into I1 and I2, and then both of these get combined at the end. So we can, of course, calculate this using Ohm's law. We can say, V equals I times R. We know V and we know R, so I1 is going to equal V over R1, and I2 is going to equal V over R2. And in both of our cases, R1 and R2 are both 4.5, I guess we can imagine for the first case, 4.5 ohms. So starting with 9 volts or 9 units of pressure, what we get is I1 equals I2, which equals going to be 2 amps. So what we see here are 2 amps. So now what we want to do is imagine is there a way we could simplify this rather than just looking at this in terms of, 2 resistors in I guess parallel. We could imagine this as one resistor. This is 9 volts and this is a question mark. Well, we know that the current that's dissipated here needs to be, so this is going to be I. The current that's going through this resistor is going to be the same that we calculated going around. So this is 2 plus 2, because, here, this is, if this is 2 and this is 2, then this must be 2 plus 2. So this must be 4 amps. And we know that all of these 9 volts must be dissipated across here as well. So what we actually see here, this resistor now has a resistance value of 9 volts over 4 amps. And of course, if we do this math, 9 divided by 4 is 2.25. So this new R, I'm going to just call this R prime, is going to equal 2.25 ohms. Now, we started with 2 resistors that were larger and we got one that was smaller. And if you take a moment to think about this, I think this actually makes sense. Basically what happens is this water has 2 paths it can possibly take, and it divides itself among each of them. So the overall resistance that we see from this entire system should be less than either one individually, because even if one of these was really, really, really high, it could always take the smaller one and then eventually go, maybe some would go through this other one. So it's always better. Now, one analogy you can think of is traffic. It's always better to have 2 lanes than 1 lane, even if one lane is really, really slow. If the other one is really fast, you're still going to get some marginal benefit of having 2 lanes because the cars are going to try to distribute. They're always going to try to pick the shortest lane. And similarly, even if one of these resistors is really high, we should expect the overall resistance of the combined parallel series to be always less than the individual ones. And likewise, when they're in series, you should always expect the sum of those to be larger than any of the individual ones. So that's one particular sanity check. Now, what happens if these resistances weren't the same? So say that R1, now let's do this in a different case. So we did case 1. And now I want to modify this example and imagine that now that we've done this, this is case 2. R1 equals, well, let's just try to keep it simple, 1 ohm, and R2 is going to equal 2 ohms. Well, as we did before, we can calculate, because we know the voltage that's basically dissipated across both of these resistors, we can then, of course, calculate what the currents are. So just using Ohm's law, we're going to say I1 is going to be 9 volts divided by 1 ohm, which is going to equal 9 amps, and I2 is going to be our 9 volts or 9 pressure units divided by 2 ohms, which is going to equal 4.5 amps. So once again, we do what we did before. We know what the flow of each of these are. We have 9 coming this way and 4.5 coming this way. So we add these together and we get that the sum, or our I total, is equal to 13.5 amps. And similarly, we can imagine what the overall resistance would look like, which is simply going to be, we have our 9 volts, and we basically need to find out we know what the current is, so this is over 13.5, and if you do the math, what you get is basically 2/3. So our R here, our total equals 2/3. And sure enough, this is less than, of course, 1 ohm or 2 ohms, which we had from before. Now, in general, whenever you have, however many of these in parallel, what you can basically do is, because you know that the current, or that the currents add together and the voltages are the same, you can basically solve these because you know the voltage dissipated across each of these is the same as the voltage dissipated across here, and the currents add. So basically what you do, if you solve this around, you get that R total equals 1 over R1 plus 1 over R2 plus et cetera, et cetera. So rather than adding, you're kind of adding the reciprocals and then taking the reciprocal of this. And once again, this just comes from the fact that what you have here is you know that the voltage is pretty constant among both of these, but you know that the currents must add together, and then current and the individual resistances that you have are inversely related due to Ohm's law. So that's why your total, if you were to, for instance, extend this into R2, R3, et cetera, is like this, and why you have this sort of reciprocal sort of relationship. So hopefully this gives you an intuition for what happens when you now have your different pieces, your different resistors in parallel.